Okay, today we will be discussing multi-layer perceptron or perceptron in general. But before that, let's quickly have a look at this. I think we saw yesterday as well, but let's just still have a look at this. The way how a neuron works is you have basically we are not talking about the entire structure of neuron here. We are just talking about where the output occurs. This is where the output is occurring in brain. So if you see quickly as the current passes through the myelin sheet, okay, there is a dispersion of ions. This is where output is happening. But if you actually see the structure of neuron, you can understand. You will be able to correlate each and every part of neuron to to the uh, to the various operations that we are doing. Okay, ignore the cell, ignore this cell. This cell is there to control everything. Okay, but look at this. So these layers, this is an entire one single neuron. Okay, even in this one single neuron, okay, these layers that you see at the end, this is where those ions are discharging. Okay, that means output is being passed to the next layer of ions, next layer of neurons. Okay, so this is where that is happening, and this myelin sheet carries all the electric signal and whatever the computation has to be done. So this is carrying the electric signal from the cell. Okay, so dendrites, axon, myelin sheet, and then axon terminal. So that much you remember for now. I will compare this neuron with the actual perceptron that we are trying to use. Okay, now perceptron is loosely, not exactly, loosely based on the neuron. Okay, we can't, we don't have technology yet to exactly replicate the human neuron, but we have somehow tried to come up with loosely the functionality of what a neuron does. So basically, a neuron, a perceptron, okay, in mathematical language, human neuron is attributed as perceptron. Okay, it's called as perceptron. Here, what you do is, see, as you can see, you have all these functionalities. These are inputs. Dendrites take the inputs from other neurons. Okay, and the very first neuron that takes the input from either from our skin or from our eyes or from our ears. So basically all of our senses are connected with these neurons. Okay, they, all those electrical signals are accepted in the very first neuron I'm talking about. Very first layer of neurons accept inputs from all our biological senses. Once these dendrites accept the input, some signal is given by this nucleus, and then that is carried throughout this myelin sheet, and accordingly output is generated here. Okay, so that is how it is. Now we have to take the same functionality and put it in mathematics. So what we have done is, we have cleverly, we already had this invention very long back. Okay, even before 1969. Okay, we already had invented gates. Okay, when someone came up with transistor, they came up with gates, right? So AND gate, OR gate, OR gate, NOR gate, NAND gate, XOR gate. Okay, so all those gates were already invented. Now what we had to do was, instead of hardware gates, we had to somehow come up with software gates. Okay, now what we did is, we designed very cleverly a layer here. Okay, we gave the ability to accept multiple inputs. Okay, nothing but x1, x2, x3 are your inputs, and w1, w2, w3, here we call it as weights. Okay, but these are essentially can be equated to slopes that we saw in the linear regression straight line equation we saw, right? So in that we saw m value as slopes. So those can be equated to these slopes only. Okay, so weights we equated. Now we converted this into mathematical simple calculation, and that calculation is wx plus b, nothing but straight line equation only. y is equal to mx plus c, right? M is w here, c is b here, x is all your data frame values. Okay, so if this is your data frame, I think I have not printed the data frame output, but anyway, so when you accept that pd.read csv and then you print the df.head, you get some output, right? Um, that would be your head. Okay, let me just do that now. Um, let me just do it so we can quickly. Okay, so we have loaded the iris, we have checked the sample. Okay, we can print somewhere here, data set dot head. Okay, this is what I'm talking about. So from id till petal width cm, so all these don't include the species one. So from id to petal width cm, this will become your x. This matrix, entire matrix will become your x, species will become your y. So adding that here, so these x values will be the values of your actual data frame. W values is something that you will have to find out. Okay, how you will find out, again we'll talk about that. Once you do the dot product here, matrix, simple matrix multiplication, then you can get the output here, final output. So essentially your perceptron is a very simple matrix multiplication unit, which is loosely based on this neuron. This is what it is doing here. It is accepting multiple inputs, doing some calculations, and then sending the output to various other neurons, and this is all happening in some milliseconds of timing. Okay, so that is what we have come up with. This is one single perceptron. Okay, so as you can see, the function is wx plus b, which is straight line equation, where w are called as weights. Okay, weights are the nothing but very slope values which we don't have. We before doing this mathematics, we have to determine the value of x. That much you remember for now. I will come how we will determine and all of that. You have to determine before multiplication, okay, and multiply with x and get the output. Okay, up until this point, is it clear? It's a very simple concept only. Okay, moving on. Yeah, so moving on now, how would we enhance this information, whatever we have discussed? So this you can get some idea here. So basically what we do is, what you see here is a simple binary classification is happening. The same thing that linear regression does, or decision tree regressor does, or random forest tree regressor does. So all those binary classifications are being done here. Okay, the best part is you don't have to do any feature engineering. Okay, no feature engineering required. You just pass the input. Okay, pass the input, then somehow you have to determine the weights, multiply that and take the summation, and then you get the output as a classifier, a line that can segregate. Okay, see the where it stops. See, it stopped here. It is able to segregate the both the classes. Okay, so it works like it all depends on two things now. So there are two variables in this. Okay, first thing that is not known is the weights. Inputs we know, input is anyway given data. Okay, and w we don't know. W we have to find out what w is. Okay, second thing is, what is this summation happening? So we call it as activation function. there are different types of activation functions that do the some addition part. So going back to this equation, if you pay attention, first you have to multiply w with x. You have to do, you're doing matrix multiplication here. Okay, dot product np dot dot. Okay, np dot dot of w comma x. If you do, you will do get the matrix multiplication. Then you have to add something. Okay, so if you do the if you pay attention here, that is what is happening. X is multiplying with w1. So basically the equation is becoming as w1 x1, okay, plus this summation is adding that up, plus w2 x2 plus w3 x3 plus w4 x4, and finally you get the output. Okay, this way a basic perceptron is working. So we will talk about weights and we will talk about perceptron, the activation function. Okay, now the basic formula is this w1 instead of wx, which was generalized as we saw from above. The formula becomes w1 x1 plus w2 x2 up to finally you also add the little bit of noise. Okay, so updating the weights that I will talk about. Okay, but first understand, so there are weights, there is bias, there is learning rate. Now we have to talk about, you can say there is one thing that is happening, one difference here. In linear regression, what essentially happens is you will take the entire data, right? You will try to, actually you will take the data row by row, okay, and then you will start calculating the y prediction value, and accordingly you will come up with the line. Initially that line won't be the best fit line, okay, then you will retry the same process, okay, and that is how for after multiple tries you will reduce the error and you will have the best fit line. Okay, now the question is, if I supply all the x1 values, x1 to all the values here, input values, and let's just say I also determine the weight values, how am I going to reduce the error? That is question number one. How will I reduce the error? Because in the very first attempt it is not necessarily it will give me the best fit line, right? So if you just multiply these weights and do some summation, not necessarily it will give me the best fit line. So how will I reduce that? That is question number one. Okay, question number two is how would I know what weights to take? Okay, question number three is what do you mean by summation here? Is it just the plain addition? If you keep adding, if you just add the plain addition, I don't think it will give you the best fit line. So those three questions we have to look at. For that we have a concept called learning rate, the same one that we already learnt in gradient descent. The same concept exactly. So exactly the same concept, everything will repeat now. Okay, so in the very first attempt what will happen is, okay, first iteration, okay, what we will do is we'll supply all the data and randomly initialize these weights. We will take randomly, we already discussed this, right? So there are various different methodologies in which you can initialize the weights. Okay, different heuristics to initialize the weights that we already saw. One of them is random initialization. We will randomly pick certain values, multiply with x, okay, and then take the summation and see what the result is. Result is obviously it won't be same as Archana, do you have a question? Because have you raised your hand or do you have a question? Yeah, tell me. Yes. Yes, we will talk about that. Okay. Understand the flow for now. I will come to feature engineering part. Okay. Um, so yeah, I will discuss that. So first, let me complete this. Okay, I'll get to your question. So here, x values multiplied by W, not necessarily activation will function will give you the best fit line. That is in the first iteration. Now what we do is, because we know it doesn't give the result in the very first attempt, so we have something called epochs. Epoch is nothing but you pass the entire training data set to these neural networks. If you pass it one time, it is called as one epoch. If you pass it 10 times repeatedly, one by one, okay, then it is called as 10 epochs. Sometimes these neural networks will run at even 100 epochs. 100 times they will take the data, reduce the error, retry with different weights, and then recalculate these values, and then try to fit the best fit line. Okay, same exact process that happens in linear regression happens here as well. Okay, it's just that the way how these weights are selected is different. Activation function is something that is new. Okay, and error calculations is slightly different. Now let's talk about how things are happening. In the very first run, we already know, okay, it does the math, it compares. Now after it fits the best fit line, that best fit line won't be the proper line, so it will calculate y cap. We already have y values, correct? We have x values, we have y values. It will start comparing these results with y values, and thereby it will take the difference, mean absolute error, mean squared error, root mean squared error, the same ones that we discussed yesterday. All these metrics are based on whatever the metric you select, it will calculate the difference, and the difference between y and y cap is called as residual. This also we talked about. Those residuals are calculated. Once the residual error is high, that is where this learning rate comes in. So what essentially happens is, there is something called as back propagation. Okay, back propagation means, now you know the weights that you chose to multiply with x are not giving you the best result, so you have to modify this x. So what happens is, differentiation of x happens, differentiation of these weights happen. Let's just say initially my w was 5, and multiplied with, you multiply the learning rate is very small value, 0.01, okay, into the weight. Let's just say 0.5 was my weight. Now what happened, this is 0.0, initially your weight was, in the very first attempt you selected the weight was 0.5. From there you are gonna multiply this learning rate with the weight that you had selected, so that you can reduce this entire value by small little bit. From 0.5, if you reduce 0.05, you will get 0.495, if I am correct, 0.05. okay, so it is 0.45. okay, so if you add 1 to 0.5, yeah, it seems to be correct. So now your weight initially was 0.5, now your weight becomes 0.45, because you took something called learning rate, and you multiplied with learning rate, you multiplied with the weight, and that amount you subtracted from the original weight. Okay, and this process is repeated for all the epochs. That is how weights are, learning rate is helping you alter the weights. Once you get the best weights possible, okay, then you would have essentially solved the problem. Okay, so that is what is happening. Just for the foundation, that much you understand. We'll go into in depth into the algorithms. Okay, so this is how learning rate is helping. Next is activation function. Now activation function means, every time it does the summation, okay, somehow you have to keep the ones, okay, that are giving the end result correctly. And sometimes what happens is, this activation function, while it is computing, I'll explain how it works, but but just understand, when it is working, it will either give you the output as 1, or it will give you the output as 0, or somewhere in between. Okay, 0 to 1 range or -1 to 1 range, it will give you the output. So sometimes we, in order, if we get negative input, we have to remove that input part. We have the output part. If we get the output as -1, that is not helping us in reaching our end result. So we have to ignore that. That's why activation functions, different activation functions have different ways of working. But I'm just saying, wherever the end output is positive, more than 0, it will keep it. If it is less than 0 and 0, it will remove it, it will ignore that. Okay, so that is the job of activation. Activation is like a filter, more like a filter, wherein which it will keep only the positive results and remove the negative results. Okay, so as you can see, this is the entire working of a perceptron. So what is happening here? There is one function which initializes the weights, these weights. Okay, learning rate is selected with some value. Now final activation, you see what is happening in activation. If the answer is 1, okay, if the net result is greater than 0, then you keep the answer as 1. Look at the condition first. If the net result, net output is greater than 0, then you make it as 1. Otherwise you make it as 0. That means anything greater than 0 is kept, anything less than 0 and 0 is removed. We don't want those. Okay, that is the job of activation. It acts as a filter. Next, in neuron, in the actual summation that is happening here, what is happening is just a very simple dot product. So you're taking the weights, whatever the inputs you have, you're doing the dot product, and to that you're adding small error. Okay, and you're returning that result, final result. Okay, next, this is what I was talking about, propagate. Propagate means basically you're just, here we are not seeing the back propagation, I will talk about that, but here you can see simple forward propagation. So nothing but propagation is nothing but you just process the results into this architecture. Okay, and you return the activation, you return the final end result of that processing. That's what is propagation means. But this propagation is called as forward propagation. There is no backward propagation given here. Forward propagation. So in the training phase, what is happening? So basically output is obtained by taking the inputs and putting it in this calculations. Okay, and weights are updated. Now weights, what are weights? Weights are nothing but you look at the output versus actual original output versus the output you have obtained, you subtract that, you multiply with the learning rate. That is what we did for weights as well. Okay, weights, for that is exactly what we did. And these weights you multiply with the x, okay, along with the original weights for all the rows of data. And then learning rate also you are doing the same thing. Learning rate also you have to modify. So for bias is how you are calculating bias is learning rate into, sorry I said learning rate, bias also you have to modify. Okay, decrease the bias. So learning rate you also you are multiplying with this residual. This is called as residual. Okay, finally you are calculating the error by subtracting from the original output. Okay, absolute value you are taking. This is called as mean absolute error. You are calculating mean absolute error, you are returning the error. Very simple code only. It's just that it is written in object oriented format. Okay, the same thing that what we learned and explained here is what is being done here. Simple perceptron. Okay, now let's take a data frame. This data frame, some random values are there. Let's see how this can be used. So this x1 is there. Okay, x2 is there. Okay, now we have to, if you plot it, it will look like this. If you plot, one is I have plotted as yellow, sorry blue, and another one is red. Now initially weights, initial weights are, we are adding some weights. Initial bias also we are adding, initial learning rate we are adding only for the sake of this example. Okay, otherwise we will randomly initialize the weights. We will ask the model itself to initialize the weights. We won't specify any weights. For only for this example we are giving the weights for the sake of this example. Okay, anyway, so once you give all these weights, now the single perceptron is taking all these values. Okay, this is just for displaying, ignore that. Now in the training part we are asking it to do the training. Okay, training function is called and weights are calculated. Okay, and then we are just plotting it. So in the first training part, as you can see, it is I'm not sure if you can see the yellow line. Yellow line is here. I'm sorry, I think it's not very visible. Let me see. Color I will give as black. Let me give the color as black because it's not visible. Unintended. Did I modify something? Where is the unexpected intent? This one. Now you can see the black line. Initially in the first training, when all the data is fed to the perceptron, it will take x1, it has to do the x1 multiplied with all these values that we have given. We have given the initial weights as 0.10, 0.1. So in that formula, w1 x1 plus w2 x2, it will start multiplying 0.1 into whatever the x value, 0. This value plus 0.1 into this, 0 plus 0.1 into this, plus 0.1 into this, plus 0.1 into this. So this way it will multiply here. Okay, so it will start multiplying that way. Actually initially it will take 0.1 into this plus 0.1 into this. That will be equated. Okay, x1 basically w1 x1 plus w2 x2, and it has come up with the line here. In the second iteration itself, as you can see, it is able to segregate, do its job well. Actually in the very first second iteration it has done the job. For third it has done here, fourth, okay, fifth, sixth. So slightly in the sixth iteration it has gone out of the error. This can happen in neural networks. Seventh, 8th, 9th, 10th. So finally at 12th stage it has come up with a proper decision boundary. Okay, but not necessarily 12 is your final answer. That also is something you have to keep in mind. Maybe 5 is good enough for us. Okay, 5 is good enough, or even 9 is good enough, because 9 seems to be the point where it is error seems to be very less. Okay, so this way it divides the, it creates a decision boundary, and decision boundary is nothing but your slope. Okay, 12 epochs, yes. Okay, so different, see, sometimes in neural networks this is this you will get to see when you run a neural network. Initially the error will be high, it will reduce up to certain point, and then it will start increasing. Error will again start increasing, and that happens because of learning rate parameter, because of gradient descent. That we will learn again how that works. Just to give you, if you want brief idea, I can show you here. It's because of this learning rate. Initially it will be here, right? Learning rate, we will give some certain value. This is what we discussed in Hessian matrices also, right? In randomly you will initialize the m value, weight value, and from there it will start decreasing up to certain point. As soon as it reaches its best point, sometimes it can even go upper side also. And if it goes upper side, automatically your error may increase, your prediction may be not as accurate as it was. So that's why this is just a normal thing in neural networks. Of course, we have certain ways that we can mitigate that. That also we will discuss. Okay, this what we discussed here is single layer perceptron, because we have taken weights. Okay, did you understand this single layer perceptron? The functionality, at least. Mm-hmm. Sorry, come again. Uh-huh. It will. Yes. Yes. This is the output. Activation from it is the output. See, we have, see, simple, very simple. For logistic regression, we had to use sigmoid. No, we had to use sigmoid in order to calculate the probabilities. There, what we said, anything above 0.5 is 1, anything below 0.5 is 0. That is what we said. Okay, that is sigmoid function. Okay, the same sigmoid function we will use here also, but what I'm saying now is very similar to that. What we are saying is anything 0 and less than 0 is 0, anything greater than 0 is 1. So our values, if there is a positive value 0.5, sorry, 0 and above, that will be 1. Okay, so that is what the activation function will do. It will do some sort of filtering and it will give you the output as either 1 or 0. It would be very similar, not exactly the same, but it would be very similar. We will discuss different activation functions. Okay, then you will understand better. So different activation functions are there. Okay, as you can see, sigmoid is also one of the activation function. The same exact sigmoid function that we learnt in logistic regression is also one of the function here. You have tan h, you have ReLU, you have LU parametric. Okay, leaky ReLU. ReLU is the most preferred one, by the way. Okay, ReLU is the most preferred one, and then you have linear also. I think that is not shown here, but there is a linear activation function also. Oh, there are many more. Here it is. Linear activation function is used for classifications. Logistic is also there. Pass is there. So a lot of things are there. Okay, but we will pick the ones that are mostly used. See, so many are there. Yes, absolutely. So there is some certain criteria basis on which we will use these filters. Okay, activation function means in your mind you think of it as a filter, filter that helps us in getting the output. If we don't have a filter, what will happen is if there is a negative value, your output will be negative only. It won't be positive. If there is a negative output, how will you determine if a person is going to default the loan? If your answer is, if you are getting the answer as 0 minus 0.5, okay, instead of 1 and 0, if you are getting the answer as minus 0.5, how will you know whether what will you even understand from that, whether to allow him to approve his loan or reject his loan, right? So that's why we have activation functions. Okay, so anything, if it is minus 0.5, it will say okay, reject his loan, because it will make the value as 0. If it is 0.5, okay, not negative but rather 0.5, 0.4, then it will make the answer as 1. Okay, there is a chance this person can pay off his loan, give him the loan. Okay, that way the answer will become 1. So that is what activation function is. Okay, but at least up until this point, have you understood? Okay, all right, let's look at very simple demo on how neural multi-layer perceptron works, and then from there we'll take it up. From there we'll dive deep. Okay, see, this is an image. Whatever you're seeing here are images. Notice the brightness where I am modifying here. Notice the brightness. If it is dark, you have to remember this concept, by the way. This is going to help you. This is a image. Okay, this is a simple image. If it is black color, that means its brightness is towards 0. If it is white color, its brightness is towards 256. Okay, so that much you remember. So I have modified the brightness of this image input. Now keep watching what happens to these x values. Pay attention to x values. So as you can see, each box is one value here. How many? 25 values are there, so 25 values should be here. Now let's just say I want to draw 6. I will increase the brightness of this. The moment I increase the brightness, see, x value is getting modified. I'm trying to draw 6. For now, you only pay attention to x values. See, so this is how it looks like. So this is an entire array. X is entire array. Actually, it's a data frame, but that data frame will be converted to array. Okay, so each time we have given x value is modified, rest of them are 0, but I will simply add certain noise. See, 0.1, 0.1 got added here, 0.1. Some noise I'm adding to confuse the MLP, multi-layer perceptron. I want to confuse it, but I want to still give me the right answer. So that's what, based on the brightness. Now this is the x value. Okay, x value, notice the w values now. W values will be randomly selected. Now I'm going to modify this x value again. You pay attention to this one. Okay, pay attention to this one first. W values are randomly chosen. So you pay attention to this one. Here the modification is happening. I'll increase. See this line is getting brighter. If I make this line brighter, see another line got brighter. Okay, I will reduce the brightness. Here let's just say I want to make it as 5. Okay, I want to make it as 5. Now it is 5. So some line got modified, no? So essentially what is happening is, each time you modify input, the output that is going here. So basically what it has done is, it has randomly chosen these w values. Let me refresh this page and then you will see. Okay, now let me start drawing the same thing. Watch what is happening here. And there is no w, by the way. I'm gonna name this image as 6. Notice w here. Or maybe I will draw here. Okay, these are my x values. W values are not yet computed because they are not yet initialized. Okay, they have to be initialized. But did you notice how these lines came to be? Which neurons got activated, which got deactivated? Okay, now I have to choose what should be my W, whether it is to be 0 or whether it is to be random. Okay, random is not working for me. Let me try with 0. Maybe increase some brightness here. This perceptron thinks this image is not 6. Okay, it made a mistake. Okay, it thought this image. Okay, maybe I will do one thing. Hold on. I think we have to use the full image or something. I will use like this instead. Okay. Okay, see, it computed, although if you can see the weights here, it has slightly initialized 0.7, 0.85, 0.6, 0.65, 1 something it has initialized, and finally it has computed the summation, and the final answer it got as 5.54, which is greater than 0. If it is greater than 0, now it considers it is a 6 number. Are you following? So these are x values, these are randomly chosen values, w values. You are multiplying these two, and then you are adding the summation here, and once you get the summation, the final value is 5.54, which is greater than 0. That is the job of activation function. So now activation function says yes, it is the value is 5.54, hence this image is 6. So we can modify this little bit. Okay, and let's just say I will add a value here. Now this is not 6, this is 3. Okay, okay, so here you are initializing the connections to 0, so everything should be 0. Let me try again. Maybe I will name this label as 3. Now see the weights, what happened to weights. It is doing the mathematics. Now you got the final value as 4.77, hence this image is 3. Okay, now I will add few more. I will make this image as 8. Now see, different neurons got activated, different weights, and weights can be negative, by the way. So you're adding, subtracting, something is happening here based on the brightness, by the way. Here 60% brightness. If I alter this to 100%, if I keep everything 100%, it should give me best results. Okay, I will still type this as 8. Okay, it start recomputing. Okay, which is greater than 0, hence it thinks it's this image is 8. Okay, see, there are 3 different values. See, one was 3 that we passed, another one was 6, another one was 8. Out of these 3, it thinks this is very resembling to 8. So if I reduce this brightness, and if I reduce this brightness, now if I pass 3, okay, now watch the computation. Okay, now it doesn't think it is 3, it made the mistake. Anyway, it still thinks it is 8, but you have to understand this is only one single layer of neuron. Okay, that is why it's doing that mathematics. Sometimes it can make mistake also. Okay, that's why we have multi-layer perceptron is there for the same reason. Okay, I increase the brightness. Now it thinks the answer is, where did it, no, it still thinks the answer is 8. Okay, never mind. But you get the idea of how it works, right? So we only pass the inputs here, we didn't do any feature engineering, nothing. So the inherent property of this neurons is, because it does the calculations at row level individually by multiplying it to the weights, it doesn't require much of pre-processing. Only few steps might be required. First step is the inputs itself. Okay, anyway, we'll talk about the feature engineering in depth. But did you understand, guys? So are you following how it is doing all the mathematics? Okay, all right. So another one I wanted to show you, this one as well. This is where I wanted to talk about various activation functions. Anyway, no, I wanted to show you just, but we will talk about them in depth later. So let's just say my x is here. Here there are two colors. Binary classification has to be done. Okay, here we are trying to see how the what is the impact of activation functions. In the very first step, I want to add the activation function as sigmoid. Sigmoid is yes shaped. Okay, weights you can modify however you want. Negative weights means it is kind of not able to understand what it is. So positive weights means it can draw the proper boundary. Okay, so this also positive. This is modifying the what? This is also actually a slope only. Okay, along y axis. I'm gonna keep the error rate as low, or somewhere in close to 0. Okay, I'm gonna choose sigmoid only. Here also I will choose sigmoid. Now see what happened. Sigmoid, see, first of all, sigmoid is S shaped curve, right? So S shaped curve means these are the rows that are at the bottom level, or maybe above level. Okay, close to 1. That's why z value you notice 0.995. Here you notice z value is 0.5 and below. So it is coming up with the boundary at z value 0.74. So basically it's saying anything above 0.74, I think this value, anything above 0.74 will be classified as one class, and anything below that value will be classified as another class. Okay, so sigmoid is still not able to draw the proper boundary because there is a overlap of colors. Okay, let's try with ReLU. So ReLU also is giving very let's just say this is step, no, not step, ReLU only. So if you give step ReLU is not able to even give proper boundaries. It's kind of a mix up. Okay, let's try with TANH. See, TANH comes very close to giving the boundary, for creating the proper boundary for this particular values, whatever the values that you have here, 6.2, 3.4, 0.1. Okay, let's try with step function. Okay, now you see it has drawn a stepwise boundary. Okay, stepwise boundary is drawn. So how it is doing all this is, it is simply taking the weights, multiplying with the actual values, okay, of the colors, and once you multiply that you will get certain value, and then to that you will add the b value, which is what we have passed here. So nothing but w1 h1, that is 6.2, into x value is color value. Okay, here it is -1, here it is minus 0.3, 0.5, that way color value, and add this to that. Finally, once you do all these h, v, z calculations, finally it's gonna come up with a, actually it's not shown here, but it is going to pass those values into various activation functions that we have selected. Here it is, we have chosen step, TANH we can try, or we can even try mix up of these. See, ReLU you can try, step you can try, here also you can pass step and ReLU is giving such results. Step and TANH, step and sigmoid, step and none, step and ReLU. Okay, next is sigmoid, next is TANH, ReLU. Okay, different options you can try to get a proper boundary. Okay, So in my opinion, for this problem, stepwise is working. Okay. Anyway, so let's deep dive into the actual learning of MLP. All right, we will learn about MLP for iris database or data set, but I want you to take a quick 15 minutes break and please come back. It's 10:25 now. Please come back at okay, come back at 10:45. Okay, come back at 10:45. We will continue the class till 11:30 or 12. Is that fine? Okay. All right. Yeah. Thank you.